Hi everyone, this is Arnoud, WizBiz.com, and welcome to this video where I play around a little bit more with these LED traffic lights. One of the things I've built with it is this LED demo model, but I have also used these little LED traffic lights in a traffic light controller with an Arduino Mega Pro Mini. That's this little thing over here. Let me connect that and start that up. So here's the microcontroller we already talked about a little bit more in a former video, and these are the touch switches to choose the control sequence. It even gives me access to this basic blinking mode. Nothing fancy there. So let's stick to the real traffic control cycles for a moment. We already saw that a touch switch even allows the switching between control cycles as found in the different countries. This way, the red light jumps directly to green. Hope you can see. And now it operates like the lamps control cycle we have over here in the Netherlands. And in this way, the control is more like in many other countries where the orange light first accompanies the red one before it enters the green cycle for that traffic light. The Dutch lamp sequence is more or less an exception, I think. This sequence in which the yellow light burns together with the red is more common, I believe. It's also how traffic lights work in many other countries in Europe, such as Germany, Austria, Switzerland and many more, like Sweden for instance. And I even have been told that the traffic lights in Russia seem to follow that pattern. Although I hope you understand I don't feel any need to go there and check that. Engineering models like these continue to capture the imagination. So once I had created this microcontrolled traffic light control system, I decided to survey the historically preceding methods as well. This exploration taught me a lot about the different possible switching solutions. Because I have received several enthusiastic and positive responses to both the YouTube video and to the various maker and technology fairs where I have demonstrated these traffic lights, I have decided to make 2 more videos to cover the historical preceding electrical and electromechanical traffic control principles. So let's talk about manual and electromechanical control in this video, and control with conventional electronics and logic gates in a future sequel. So let's go back in time a little bit in our imagination, and well, talking about imagination, I imagine it all started once with a manual operated control. For example, with a rotary switch with multiple positions like this one. This one is from Fischer Technique, my favorite construction material. And with this rotary switch and an additional push button like this one, a basic traffic light control circuit can be made. I came across such a circuit in the model booklets of the Fischer Technique EM2 construction kit. To operate the extra additional switch, we have to place a handle or a pointer of building blocks on top of the rotary switch. The handle also connects the 2 opposite contacts of the rotary switch in each step. So when we loop through 4 neighboring connections with the power voltage, the handle just connects to the opposite side in each step. And it brings the supply voltage to one of these 4 opposite contacts in each successive step. And on this opposite side we might connect the 4 different colored lights. So the power supply is connected to one side of the rotary switch and the 4 lamps go through the other contacts of the rotary switch. And the handle, it just connects one of 4 of the lamps to the power supply in each successive step. Alright, let me explain this basic traffic light control using an illustration from an old Fischer Technique engineering hobby book. In it, the rotary switch I just showed is used. It's shown here schematically, and in addition to the rotary switch, we also see that the example uses an additional push button that's operated by a protrusion of the pointer. We saw a moment ago the little handle that's attached to the rotary switch. Before I go into more detail, let me explain the matrix on the right. It's showing the 4 different stages that the lights of a traffic light or a single direction of traffic would go through from green to red and back to green. There are basically 4 phases it's looping through, 4 different stages, where the odd stages number 1 and 3 are usually longer in time than the stages where the orange lights are on. That'll be the even numbered stages, number 2 and 4. Also visible in the matrix is that in this sequence the orange light first joins the red light, so it's on together with the red light before the green light takes over. So in that phase both of these lights are on. This is not the case in every country. I'll come back to that in a moment. Let's see what happens in position 1 of the rotary switch if I set the rotary switch so that it connects points 2 and 6 in the illustration. Then we actually get stage 1 of the traffic light control, and in it only the green light is on. If we continue turning counterclockwise to stage 2 of the traffic light control, the contacts 1 and 5 are connected and only the orange or the yellow light is on. If we turn another turn counterclockwise, one more position, we get to stage number 3. This is stage 3 of the traffic light control, in which only the red light is on. And now something special is going to happen, because if we turn one more turn, we arrive at stage 4 of the traffic light control, in which the yellow light joins the red light. This is achieved electrically with the extra switch, the red wire in the original diagram to the left. So, when the yellow light is connected via the rotary switch, the extra switch also lights up the red light at that moment. If that is done and we turn one more time, we automatically arrive at stage 1 and can go on forever and ever, and so on and so on. Alright, this is of course quite a simple manually operated solution. The circuit diagram takes the 3 lamp colors rather than the various phases of traffic control as its starting point. The rotary switch can be rotated through 4 positions, but it allows traffic light control for only one single traffic light. However, if we want to control 2 traffic lights or traffic directions simultaneously, this method falls short, because the light phases leading to the red light and the one leading to the green light in the cycle are not fully complementary in terms of the yellow lights in between. One traffic light just adds the yellow light to the red light for a moment, while this is not the case with the other green light in the other traffic light at that very moment. Therefore, a single connection for these 2 lights of the different traffic lights is not possible. This would require at least a secondary rotary switch and another additional switch, and as a result 5 independent lamp stages should be able to be switched, which is of course not possible with a 4-step switch like this. Perhaps it makes more sense not to use the different switching possibilities as a starting point, but to use the 4 different steps in the control sequence as a starting point. Then we would only have to count from 1 to 4 and decode which lamp in the 2 traffic lights should light up in each step. The classic circuit diagram showed how one traffic light can be controlled manually with a rotary switch from Fischer Technique. But by adding a pair of semiconductors, such as the 6 diodes in this circuit diagram, we're able to control 2 traffic directions with the same rotary switch. We can thus control 2 individual traffic directions and 2 traffic lights with the same simple 4-position rotary switch. Because the diodes conduct the current in the forward direction and block the current in the reverse direction, we can make so-called wired ORs with them. This makes it possible to define multiple one-way routes to a lamp that are logically ORed. I did some puzzling and I finally came up with this. Let's go through the different positions. Suppose we activate phase 1 with the rotary switch and thus light the red lamp in the traffic light 1 and the green lamp of traffic light 2. Then this red colored wiring is active. From traffic light 1 the red lamp is lit, from traffic light 2 the green lamp is lit. In this mode 2, phase 2 of the traffic light control, both orange lamps are lit. From traffic light 1 the red lamp is still switched on. Some of the diodes are switched in the forward direction. These allow the current to go through. The diodes that are now in the reverse direction block the current and keep the connected lamps off. Let's look at phase 3. This is phase 3 of the traffic control diagram, and here we see that the green lamp of traffic light 1 has just turned on and the red lamp is burning in traffic light number 2. Again, there are diodes to ensure that inapplicable lamps turn on at the same time in this phase. Finally then we get phase 4 of the circuit diagram. Here we see that the green lamp of traffic light 1 has changed to an orange lamp to indicate that we're about to get the red light. And from traffic light number 2 on the right, the yellow lamp and the red lamp are burning together. And that completes the entire control cycle. So in this way it is possible to make a complete traffic light control for 2 directions of traffic with the same old familiar rotary switch with only 4 switching positions. In other words, it's efficient by thinking in phases and making a decoder that decodes which lamps are lit in each step. In this model the 4 different steps still have to be made by hand. The main thing is to go through the 4 different steps sequentially. This switching principle can of course be motorized and therefore automated by having a motor operating the rotary switch. So we could also make something like this. Here the successive contact phases are programmed with cams. The challenge of course here is that these 4 phases follow each other as precisely as possible, without any gaps but also without any overlap. From this point of view, this phase sequencer or counter is similar to the manually operated rotary switch. So it can also be used with the same decoding wiring with the diodes we saw a moment ago. However, such a mechanical 4-step counter remains prone to error. If error occurs in the programming due to mutual twisting of the cams, this will lead to errors in the control of the lights. There is the same disadvantage with the switching gaps of the rotary switch, and there will also be dead moments between the switching positions, just like with the rotary switch. At these moments, of course, no lamp burns. This method, with the cam disk over here, additionally introduces the problem of overlap of the steps, which at those very moments causes unwanted lights to be on at the same time. So what it comes down to is that the 4 steps actually need to be completed as cleanly as possible, without any gaps or overlap between the switching steps. I think this will always be the weak point of a manual or electromechanical solution like this. In the development history of traffic controls, these solutions feel a bit like the early days, and the microcontroller controls discussed earlier feel like the other end of the spectrum. To paint the complete picture, it feels like we have to investigate whether we can go through the 4 control steps with conventional electronics. It's a nice challenge to build such a traffic control with basic electronic modules. In fact, This 4-step counter can always be built with old-fashioned timers, where the decoder of the lights is built with logic gates. I'm looking forward to investigating this, and of course I'll hope you join me again if this leads to another video. If you find these videos interesting, by the way, don't forget to subscribe or leave a thumbs up. In the meantime, I'll continue playing with these traffic controls and tiny LED traffic lights. So for now, it's a see you again and a well-meant happy hacking!